Hi, my name's Kevin Cogger, and I'm a software engineer on the Xbox Advanced Technology Group at Microsoft.
Hi, my name is Chuck Walborn. I'm an engineer in the Microsoft Game Development Kit team responsible for Visual Studio integration and tools. Today we're going to be talking about the latest version of Visual Studio, as well as some technologies related to building without install. I also want to talk a bit about the support for the Clang compiler. So after wrapping up my portion of the talk, Kevin will take over and talk about building without install. He'll talk a bit about Docker containers and ongoing support as well. So let's start with the latest information about Visual Studio. This year, Visual Studio 2022 is released, and the big feature here is 64-bit native version for the IDE. This is a feature we've been asking for many years, so it's very exciting to see it finally release. In addition to the new IDE, the Microsoft Visual C++ compiler has a new version. This has been hosted for x64 native for many years. And the March 2022 GDK now supports Visual Studio 2022 and all of its various platform toolsets. The 64-bit IDE has been a fairly consistent request from game developers for many years. We've had it brought up in Q&A with the Visual Studio team, on the forums, and many other feedback. And now the IDE is 64-bit native in Visual Studio 2022. It is important that this switch does have a few consequences that you should be aware of, and I'll go through them now. The first one is that all the extensions, the physics extensions, have to be x64 native compatible. If you have a C# managed assembly, typically if it's built any CPU, it'll just work. Any native code needs to be provided in x64 native. The 32-bit version will not work with this IDE. The other thing to note is if you're doing any Visual Studio extension development, the SDK is now on NuGet rather than being part of the Visual Studio install. If you have custom Visual Studio extensions, the first thing you're going to do is modify the manifest. This specifies which versions of Visual Studio it supports. For x64 native support, you provide the Visual Studio 2022 section. And if you, in this case, support Visual Studio 2017 and Visual Studio 2019, it'll have the legacy x86 architecture set. One of the biggest changes to the product that's sort of unnoticed is that MS Build is now a 64-bit process. Historically, it's always been available for both 32-bit and 64-bit, but even when you were using the x64 native developer command prompt, it was still using the 32-bit version of MS Build for compatibility. This means that if you have custom MS Build tasks, and you've not explicitly asked for x64 in the past, you may have some compatibility issues to look at. If you're doing Azure DevOps builds, there's a specific way to specify x86 versus x64, and to keep it consistent, we recommend using the x64 setting. If you want more details on this, particularly from the .NET experience, there's a Visual Studio blog post that you can reference later. If you have custom builds, you can have a couple ways of handling it for the architecture. If you have a custom process that's 32-bit only, MS Build has the facility for launching that as a separate process. You could specify that with the architecture tag on the using task. If you're using C# or any CPU builds, then it's pretty much just a straight reference without an architecture. And then if you have something that you want to support both with, you can specify both 32-bit and 64-bit versions, and the right one will get used at runtime. In the long run, you probably can get rid of the 32-bit only, but in the transition, you'll want both. So in addition to the IDE and the tooling, we now have a new version of the Microsoft Visual C compiler. The big feature here is it has support for the new C++ 20 language standard. It's important to note that C++ stood latest in the switch is now moving on to the C++ 23 draft. This is one of the reasons we recommend using a language-specific switch instead of just a generic one. Officially, the standard C++ 20 switch was added in 2019, the last update. But if you look at the CLXZ output, you won't see it listed. It is listed there in VS 2022, but it's supported in both. As we've enjoyed the last couple of releases, the C++ runtime is forward compatible. This means if you build a static library or code with Visual Studio 2017 or Visual Studio 2019, you can still link that library against a exe built with 2022. This has gone back to Visual Studio 2015 Update 3, so it really helped the middleware transition and just makes it easier to integrate it piecemeal instead of having to switch all of it at once. The Visual Studio compiler toolset now supports the C++ language standard. It's considered production ready as of the last version of Visual Studio 2019. A few things to note if you want to take advantage of the C++20 support. The C++20 modules feature requires that permissive strict be enabled. This is the default with the standard C++20 switch. If you are interested in C++20 in your studio, I would recommend taking a look at Visual Studio 2022 support. It has a more conformant implementation of C++20 concepts, but more importantly, it has quite a number of library defect reports implemented. If you want more detail on the C++20 support and the switch behavior, I recommend you take a look at this Visual Studio blog post. So one of the more interesting aspects of modern conformance with Visual Studio is that the preprocessor, there's actually two of them. The Microsoft classic traditional processor has been around for many, many decades and is still the default when you build Microsoft Visual Studio Code. There's a lot of back compatibility with headers and code that we don't want to break. There's a C99 conformant preprocessor that's accessible through the ZC switch. In general, we recommend moving to this, although you might have to do some code cleanup depending on exactly what you have in your code base. The main thing to note is that if you want to use the C++20 variable opt define, you have to have this new preprocessor enabled. There was a blog post a while ago that went into sort of the meat of the big differences. If you have existing code bases, you should try this switch and definitely clean up the errors you find. Another historical behavior for Visual Studio is the C++ macro itself is supposed to report which version of the standard the compiler supports. And it has reported 1997-11 for a very long time. And it continues to do that today because when we tried switching it, there turned out to be a lot of code that had this dependency. There's a new switch, the ZC switch, that will cause it to report the real value tied to the right standard setting. We have this enabled in the GDK template, but it's not necessarily enabled in all your code bases. It's well worth taking a pass at this and making sure this is cleaned up. The expectation is that in a future release of Visual Studio, this will switch and become the default behavior. There have also been a few tweaks in the code generation for Visual Studio 2022 that allows you a little more control over some of the floating point behaviors. For the most part, these aren't relevant to game development, but you should be aware of them, especially if you see references to these switches in the release notes. The FB contract controls how the fused multiply add operation is used. Since we're using Arch AVX2 for Scarlet development and Xbox Series X and S, then this is mostly already done. But if you're using some PC builds, you might want to take a look at the switch. And then there's a kind of subtle behavior difference between 2017 and 2019 that was then reverted for 2022 around how certain floating point to signed integer conversions are handled. Most of this is related to being conformant with the new AVX 512 instruction set. I don't want to spend a lot of time on this feature, but if you're interested in the details, it's in this Visual Studio blog with lots of technical background. A big part of game development is build times, and Microsoft and the Visual Studio team have had a lot of feedback over the years around better ways to control this. Historically, you either have single-threaded building or you have multi-threaded, and the multi-threading just kind of takes over the whole machine. This can be challenging for environments like distributed computing or distributed builds or cloud, where you don't necessarily want the builds to consume all available resources. In the 2019-1610 update, there was a feature called the MS Build Resource Manager. This is intended to give you explicit control over how many cores that MS Build makes use of when you use the multi-build option. This lets you tune it and control a little bit better about how it uses multiple cores. For Visual Studio 2022, it is on by default. It's important to note that there are some situations where it can actually slow down the build, depending on exactly how you have things set up. So it's important that if you run into this performance problem when you move to 2022, that you go back and refer to this blog post. It'll detail exactly what the issue is and how to work around it. And then conversely, back in an earlier release of 2019, there was a tool called the MTT tool. It allows you to control the number of cores that the Visual Studio compiler uses when you enable parallelism through that for the same sort of thing. So if you're interested in having your build machines or your local builds take less resources, you can use these tools to control it. And one of the things I've been working on the last few years is getting Clang LLVM support for game development through Microsoft platforms. Back in Visual Studio 2019, there was a feature added to the core product that supported Clang as a Windows first-class citizen parallel to Microsoft Visual C. There's an MS Build platform toolset defined for it. This relies heavily on the Clang CL front end, which is designed to emulate a lot of the Microsoft Visual Studio switches. And the official integration makes use of the Visual Studio version of the runtime. It's pretty easy to install. The main thing is you need to know it's off by default. You can find it in the desktop development workgroup. You can see it here in the slide at the bottom, the C++ v13 tools. There's also some specific component IDs if you want to automate this through your setup deployment. You can also access it through the individual components page, but there are some known bugs in the VS 2022 RTM, so you'll probably want to go through the work group instead. As of last April, we have official support for the Clang CL platform toolset through the Microsoft Game Development Kit. We have the documentation, covers all the details, sort of the obvious things around the architecture selection, along with a lot of less obvious details and known issues. We've been using this internally for several years in the samples, so we have a lot of good guidance in the documentation already. The main thing to note is that if you run into a compiler bug, don't try reporting that bug through us. The compiler that we're shipping is the one from the public release. So if you have compiler bugs, they should go directly to the LLVM support site. If it turns out, for example, an issue I ran into recently where you need a refresh or an update, you can always install it directly yourself, but do let us know and we can try to make sure that it gets picked up in a future Visual Studio update cycle. The actual C++ library is being used, so all the C runtime is still owned by us. So if you have concerns, you can use the forums or the Visual Studio feedback page. They do consider Clang a prime target, so if you have bugs on Clang, they will action on them. For people who are setting up their own build systems and not using the MS Build integration we provide, one of the things that a few people have run into is that there are two different versions of the C runtime at use in the toolset. By default, it uses the desktop version, but there's actually a one-core variant, which is the one we want to use for Xbox development with the GDK. The MS Build rules already handle this, but again, if you're using your own build system, you're going to want to set this up. You'll note that the header set is the exact same headers for both sets. The difference is which DLL and which link library you use. I've got the paths here, but effectively just look for the one that's got the one core in the path and you'll be in the right one. These differences can be pretty subtle. Sometimes the desktop one will just work right, but to make sure sort of long-term you don't run into any weird issues, make sure you're using this variant instead. So in addition to the Clang toolset support, we also have some samples around using CMake rather than MS Build. The Visual Studio product has supported CMake integration for a while now. And the most recent releases add a feature called CMake presets. I've been using CMake for a few years now, and this really makes it a lot simpler to use. You should also be aware the versions change fairly quickly. You can always install it externally, but this is the one that comes with the product. The three specific ATG samples around CMake are the CMake example. This one's intended mostly to fully document all these build settings and options that we have documented. You can take a look through that CMake and you'll see that it doesn't make use of any of the Visual Studio integration in the Microsoft Game Development Kit. It's designed around the Ninja generator, which basically does no work with MS Build, so this is a great way to see all the details. Even if you're not using CMake, if you're doing any kind of custom build system, you can see all the details, and we keep this up pretty regularly. For people who want to use CMake more for daily workflow, we have the CMake GDK example. This one actually uses the MS Build rules in the GDK through the Visual Studio generator. You'll see it's set up a little differently than the other one, a little less verbose, but both scenarios work well. And then for some teams, particularly technology teams, people want to run their console-based, text-based tests and unit tests on the Xbox itself. And this CMake Xbox console app demonstrates a way to do that in a way that's compatible with both the system OS and the host and the game OS. I also want to discuss a little bit about the Windows SDK. There's been a number of releases over the years. 19041, which was the one released a few years ago, is still the minimum required for all the GDKs. This has all the games partition APIs that you need for development against Xbox. There's been 2 major releases of the SDK since then. Right now, the one that's referred to sometimes as the Windows 11 SDK is the latest. This is fully compatible with Xbox development. If you're looking for C99 preprocessor usage, or you're looking at the new C11, C17 support in Visual Studio, I highly recommend you pick up the new SDK. There's lots of changes there to improve that experience. For Xbox development specifically, there's a new version of DirectX Math, and then a few of some of the weirder partition issues we've had over the years, which may have been release notes here or there. Most of those are fixed in the new SDK. If you're doing PC DirectX 12 development, again, I recommend pick up this SDK. It has a much newer version of the HLSL compiler and DX12 headers. There's also been work over the last few years to really improve the Clang LLVM conformance. So if you run with high levels of warnings, again, the SDK might clean them up. With that, I want to transition over to Kevin, who's going to talk about building without install and Docker containers as well.
Thanks, Chuck. Next, I'm going to talk about some options for doing consistent builds with fewer dependencies, which are especially suited for build servers. So when you're doing a build, typically you'll need to install Visual Studio and the GDK on your development machine for full access to the tools for development, debugging, and profiling. However, if you're setting up a build server, this can be a lot simpler if you don't have to actually install the GDK. We have a technique called build without install, which makes this possible. With build without install, you can copy an extracted GDK to your build server and build against it without having to install it. You can also check this extracted GDK into your source control. This means that you can build different branches or even entirely different projects on the same build machines because their build dependencies come down with them. Even on a local machine, you can test out a new GDK without having to install it. It's also possible to make your build environment even more consistent and reproducible by using a Docker container, which is something I'll talk about in a little while. I do want to point out, this section is a fairly high-level overview. We have a sample called BWOI example, which demonstrates all of this in action, including the use of Docker containers. In addition, our documentation goes into full detail on this scenario. You can find that at aka.ms/GDK_BWOI. I would say if you're interested in the content here and you remember nothing else, please do remember to look at the BWOI sample for more details. So when you're setting this up, you do need to install Visual Studio. However, you can use Visual Studio Build Tools, which is a lightweight edition of Visual Studio that contains only what you need to do command line builds. You'll also need the extracted GDK, which you can download from our download site or extract yourself from the GDK installer. It's also possible to extract the Windows SDK to use that without installing, although this typically isn't needed. Generally, you aren't changing the Windows SDK very frequently, so it's often easier just to install this on your build machine. In addition, you'll need to override a few MS Build properties just to ensure that your build can find that extracted GDK. So to go into a bit more detail, first we'll look at Visual Studio. As I mentioned, the Visual Studio Build Tools is a version that's particularly suited for building on build servers by providing a minimal install that contains what you need for command line builds. On the slide, you can see a few components that you might want to install when you're installing this version. Here I've specified the C++ Build Tools workload, which provides the base C++ build support. I've also specified the Windows 10 SDK, as I've chosen to install that directly on the build machine. Next, I have the MSVC v143 Build Tools. This is the version that comes with Visual Studio 2022. I've also installed the MSVC v142 Build Tools, which are the version that first came with Visual Studio 2019. And if I want to use Clang, I can install the C++ Clang tools for Windows. This is just an example of some of the components you may wish to install with Visual Studio Build Tools. If you look at our sample BWI example, its README has more details about how to set up other Visual Studio versions and configurations. So next we have our extracted GDK. As I mentioned, this is a version of the GDK that you can simply copy onto your build machine to build against. The easiest way to get this is to download it directly from the Xbox Developer Download site at aka.ms/xgddl. When you're choosing the version to download, you can look for one labeled Extracted for Build Systems. This provides a zip file, and if you unzip it, you'll have that extracted copy that you can drop onto any build server you want to use. In the future, we're also planning an option to allow you to download this from NuGet. Additionally, if you prefer, you can extract manually from the GDK installer. We provide a script to do this in the Build Without Install example sample, as well as in the documentation. This script also works on the public GDK, which is our public-facing version of the GDK that only supports Windows builds. Note that if you're doing manual extraction, this does use the MSI exec tool, which is just the tool used to run MSI installers. It takes a global lock, which means it'll fail if any other installer happens to be running at the same time. This includes things like Windows Update. This means it's typically not a good idea to do this manual extraction as part of some scripted process. If you are doing manual extraction, I would recommend doing it once while you can monitor it, and then copy that output to any machine you need to use. Also, be aware that the extracted GDK has a relatively deep path structure, so I recommend placing it fairly close to the root of your drive to avoid hitting max path issues. It's not so deep that you can't place it in any nested directory, but in general, you don't want to put it too deep. So once you have your extracted GDK on your build machine, there is one other step, which is to combine the GDK's MSBuild rules and the standard C++ MSBuild rules into a single folder. We call this merging VC targets. We have a script in BWI example that can do this, and the documentation also provides more detail on what you need to combine. With that done, you're just about ready to build. Now you just need to override a few MSBuild properties to ensure that your build will find the extracted GDK. An easy way to do this is with a file called directory.build.props. If you put a file with this name in your build root or next to your projects, MSBuild will find it automatically and use it to override properties. If you remove this file, everything works just like normal with the properties specified in their project files. That means you can copy this down while setting up your build on a build server without affecting any local builds you might do. I'm not going to go into all the details of what exactly you need to override in this file, but again, BWI example has a sample version of this file that sets everything up properly. The documentation also covers all the properties you'll need to override in detail. Once you have the file in place, you can simply run MSBuild as you normally would. The properties will be overridden automatically, and you'll build against the extracted GDK. Now, even if you're not using MSBuild, it's still possible to do a build without install. You will have to set the properties, paths, and so on to override these to point at the extracted GDK, so the exact details of how you'll do this will vary depending on your build system. For an example, you can look at the CMake example sample that Chuck mentioned. This shows how to do this using CMake, including support for build without install with an optional parameter. Chuck also mentioned that this sample documents all of the various compiler and linker switches and so on that you'll need to set to build against the GDK. So even if you're using some other build system, you can use this as a reference to understand not only how you need to set up a project to build against the GDK, but how to do build without install, even without using MSBuild. So for even more isolation and consistency, it's also possible to build your game in a container, which you might also know as a Docker container. If you're not familiar with these, containers are a lightweight and isolated virtualization system, which is similar to a virtual machine. There are well-defined processes for defining, starting, and stopping these containers. These make it easy to create a reproducible build environment by setting up a container that has all the dependencies already in place. You can deploy this container anywhere that you need to do a build. This includes things like build servers, or in the cloud with existing technology like Kubernetes. And you can also even run these on your local machine using a tool like Docker Desktop. For example, maybe you need to build a different branch or an entirely different project, and you don't have the right GDK or all its dependencies installed. You could use a Docker container that already has this set up for you. Now, containers are a pretty massive topic on their own, so again, I can't go into all the details here, but we do have extensive documentation on how these work. You can find that at docs.microsoft.com/virtualization/Windows containers. So to put all this together, next I'd like to show a demo of how to do build without install in a container using the BWI example sample. Let's take a look at that. So I've prepared a directory that contains a few things we'll need to use when building our game without installing and using a Docker container. First of all, we have BWI example. This is the sample that I've described previously. It contains a solution file, a project file, and some regular source files, just like in any other game project. However, it also contains a directory.build.props, which, as I've described, specifies some MS-Build property overrides that will be used for build without install. It also has a Docker file. This is essentially a script that's used to set up our container. This defines how the container should be built, so it has the dependencies we need. I'll go into that in a bit more detail shortly. This sample also comes with a few important scripts that we'll need. setenv.cmd sets up some environment variables that are used for build without install. And vctargets.cmd does the merging of the VC targets that I described previously. This will copy the C++ and the GDK build targets into the same folder so they can be accessed during the build without install process. We also have the SDKs directory. This contains our actual extracted Microsoft GDK. If you look at the contents, it's quite similar to what you'd see in an installed GDK. However, this version can be copied to any machine to be used without installation. Finally, this is the same Docker file that I showed inside the sample directory. I've copied it here because when I build this container, it needs to have access to both the extracted SDK and the project itself. Therefore, I want to do my container build from a parent directory containing both of these. So let's take a look at what's inside the Docker file. As I mentioned, this is essentially a script defining how the container should be set up. The first command here is from, which defines the base container that will be used as a starting point. Microsoft already provides a number of base containers online that can be used for building your own Docker containers on top of. This one is a .NET Framework SDK container. And while I'm not building on the .NET Framework, it's useful because it contains some dependencies we already need, notably Visual Studio Build tools. With that established, we also set a few arguments that will be passed in when we build our container. Next, we establish the command shell that we want to use. And then we run a few commands. The first command is curl, which will just download the Visual Studio Build Tools installer from the Microsoft download site. While Visual Studio Build Tools is already installed in this container, it doesn't have quite the right components that we need. So we download the installer so that we can modify the install and add the components we want. That's what this command here does. It runs the installer, passing in a modify flag, telling it to modify the install. First, we add the VC Tools workload, which contains the baseline Visual C++ support. Next, we add the Windows 10 SDK in the particular version that we want to build against. We remove several other SDKs that we don't actually need, just so they don't take up space in the container. Then we add the MSVC toolsets that we want. This is the default MSVC toolset for Visual Studio 2022, which is the V143 toolset. If we want to build older projects using the V142 toolset that came with Visual Studio 2019, we can add this component. Similarly, we have the V141 toolset for Visual Studio 2017 projects. And if we want to use Clang, we can add Clang support using this component. When all that's done, we just check for an expected error level, which means that the install completed. Then we delete the installer as we no longer need it. Next, we copy a few things into the container where they'll be available when we're doing our builds. First, we copy the extracted SDK, which contains an extracted GDK. That comes to C SDKs. Then we copy the command scripts out of a script directory, which we'll be specifying as BWI example. Those come into C scripts. Finally, we just need to run these scripts in order to merge the VC targets. We set our working directory to the scripts directory, and we set the Visual Studio install directory so the scripts can find that. Then we run setenv, which just needs to know what type of Visual Studio we're using, the GDK version, and where to find the extracted SDKs. Then we run VC targets. This will set a few environment variables and then merge the VC targets so they're ready to go for our build. Once that's done, our container is set up, and we simply need to establish an entry point that will tell it what happens when we run the container. The entry point will first run setenv with the same parameters as above. This ensures that every time we run the container, the environment will be set up for build without install. Next, we use PowerShell, which will run whatever command we pass into it when we run the container. So let's see what happens when you build a container, which will execute this script. Now, building this container can take a while, so I've actually done this in advance, but I'll show you the command that I ran. I use docker build, which tells it that I want to build a Docker file. I named my container GDK BWI, and I tagged it as latest. I specify memory for the container, which is 2 GB in this case. And I provide values for the arguments. The extracted SDK directory is SDKs. The script directory is BWI example. And the GDK version is the March 2022 GDK. Finally, I have to tell it which directory contains my Docker file, which in our case is simply the current directory. I've outputted the results of this to a log, which we can take a look at now. So in this log, it basically just walks through the script that I just showed you in the Docker file. We see it does from to get our base container, sets the arguments, sets the command shell, and then runs the commands, which include curl and the Visual Studio Build Tools installer. The output here is a little funny, but that's just an artifact of how curl updates the console window. When that's done, we copy these files into the container, set the working directory, and run the scripts. You can see that setenv establishes these two environment variables, which we need for build without install. VC targets then merges all of those targets into a single directory. Now there are a lot of files to be merged here, so this actually has quite a bit of output. The important thing is that they all end up here in C SDKs VC targets 170. This contains all of the MS Build targets used by Visual Studio 2022. Further down, you'll find it also does VC targets 160, which supports Visual Studio 2019. And for Visual Studio 2017, we have VC targets 150. When that's done, our container is ready to go, and it just needs to set up that entry point. Now you can see it's successfully built, and it's been tagged as GDK BWI latest. So with the container built, now we can run it. To run it, I'm going to use a command provided at the top of the Docker file. I'll also output that to a log so I can look at the results easily. Now in my run command, there are a few important parameters that I'm passing. This -v allows me to map a directory from my local dev machine into the container. In this case, I'm mapping BWI example to C project inside the container. This is important for two reasons. First, it means everything from BWI example will be visible in the container at C project. This is how I pass my source and project files into the container. It also means that after my MS Build project is built, I'll be able to grab the results from BWI example just as if I had built locally. With that specified, I can set my working directory as C project. I specify the container I want to run as GDK BWI, and then I give it a command to execute inside the container. In this case, it's just MS Build of my project with a standard configuration and platform. Now we can look at what happened when I ran that command. You can see that because I specified that setenv must be run in my entry point, setenv is always run first. It again establishes these two environment variables. After that, the MS Build command runs and it simply builds my project normally. You will notice, though, that anywhere your MS Build project might reference the GDK is now referencing the extracted GDK that I specified. For example, this is where it runs the shader compiler, and it's using the shader compiler from in the extracted GDK directory. Otherwise, this builds just like a normal MS Build process would. When it's done, you'll see that all of the output is sent underneath C project. And then, when the build finishes, the container will exit. But now, because I mapped C project to my local BWI example, I can navigate there and see that the output is right here. If I go inside, I can find the loose image, which I can now deploy to a console and run just like any other game. Everything I covered is demonstrated in that sample, as well as in detail in the documentation. If you're interested in this, please check out the sample, read its README, look through the files, and I think it should all come together. So we're going to wrap up with a bit on the ongoing support story for Visual Studio and the various versions that have been released. When the March 2022 GDK shipped, it included support for Visual Studio 2017, version 15.9, Visual Studio 2019, version 16.7 and later, and Visual Studio 2022, version 17.0 and later. However, in April 2022, Visual Studio 2017 went out of mainstream support. That means it now has extended support only, and the bar is very high for bug fixes. This is mostly targeted now at paid enterprise support customers. This means if you haven't already, I do recommend that you upgrade to Visual Studio 2019 or later at this point. Also in April of this year, Visual Studio 2019's minimum supported version became 16.9. This means if you're on an earlier version, I would also recommend upgrading that. Also in October of this year, Visual Studio 2019's minimum supported version will become 16.11. That is the final major update for Visual Studio 2019, so it should receive ongoing support for several more years. The GDK also later this year will be removing support for these older versions of Visual Studio, so please be aware of that. We'll have more details to communicate as they become available. One other improvement in Visual Studio 2022 is that you can now lock your Visual Studio to a particular update version. On previous versions, when you ran the installer, it would typically try to update you to the latest release, which could be undesirable if you had, say, a large team and you wanted to keep everyone on a particular stable configuration. With Visual Studio 2022, you can now install Visual Studio from a long-term servicing channel, which provides guaranteed security and bug fixes for 18 months, but no new features. The plan is for these to be created every even-numbered release, so for example, 17.0, 17.2, and so on. Thanks a lot, and enjoy the rest of XFest.